Hi everyone, my name is Farid Zidat. I am Senior Application Engineer within Altair. Today we want to speak about how to introduce or include iron losses in AC steady state magnetic coupled to the thermal computation. So to include the iron losses, we need first to compute a pure magnetic project in order to get these iron losses. So we have to define the magnetic project first. I took this example, a 3D example from the supervisor examples we have within Flux. Here I modified it a little bit. This target, this region, volume region is called target, and I use it as a laminated region. And the core, I divided it on two regions. The one is the solid conductor region in order to take into account eddy current inside, and the other one is simply a magnetic non-conducting region. And here we have the coil. So we have like the main region we used to see in standard Flux project actually. So here first I wanted to compute this in magnetic application. Here it's the application is AC steady state magnetic 3D application. It's already solved, and here I will go to compute iron losses. So the iron losses are defined, are computed through the menu computation of iron losses, and then here you have the choice to use the model Bertotti, or if you have defined it already on the materials, and this is the case for me. Here the material still laminated contain these iron losses parameters, right? So then I am going to select the region target, and I will call it losses. Maybe let me call it total losses. You will see why I call it total losses. And total here. Okay, so this is the total iron losses. So here the project is supplied with current sources. What I want to compute and export from this project is to export separately hysteresis losses, classical eddy current losses, and excess losses. Why I want to separate them? Because I want to make this eddy current losses depending on the temperature in my thermal project. Because since I am supplying with the current sources, I am imposing the current, the magnetic field, so the hysteresis losses will not be impacted by the temperature. I suppose only the eddy current losses will be impacted by the temperature variation, so I will make them depending on the temperature. That's why I want to compute again these three separate quantities. So once you computed iron losses, actually Flux will create these spatial quantities, and I want for my thermal project export this spatial quantity. But first let's compute this iron losses separately. To do that, I will first select target and finally the modified Bertotti model. Okay, so I have to put the parameters for the hysteresis part and put 0 for the other one. So I can compute actually only the hysteresis losses for this computation. Okay, and I will call it hist. Here I will add hist, and here I will add hist and make computation. Okay. So as you can see here, I have only the hysteresis losses computed, and if I go to the results and can, I can bring here the total losses. I can compare them. So here I have mainly the hysteresis losses computed, right? And I have the corresponding spatial quantity computed. Then I will compute again the losses for the current part only. Okay. Uh, Here I forgot to put the name, corresponding name, like in the previous one, so I can edit it and I can make EC for eddy current. And here I can also make edit it and make EC, and this one as well. Where is it? This one I can make EC as well for eddy current. Okay. Then the last computation I need is for the other part of the last part of the losses. So first I have to put 0 here, 0 for classical, and then I have to put the coefficient for the classical, for the excess losses. And here I will make excess EX and EX, and here EX as well. Okay. Then now I have all the losses computed. I will now export them. So I have to go to data exchange, export spatial quantity on a volume region target. I will call it first hist. So I will select user and select the mean value of losses for hysteresis. Okay. I will make the same thing, then export on the target, and I will call it eddy current losses. We'll select once again the mean value of the losses for the current part or classical part. And the last one will be export quantity and formula. It will be as well on the target, and I will call it EX for excess losses, and then let me select the mean value here and go to valorization, and it is here. If I go to file manager, I can see the DEX file I exported for eddy current excess losses, and normally I should find also hysteresis here. Okay. So now, once it's done, I have to open my Flux project where I defined the application EC, not this one, but the other one, where I defined the application AC steady state coupled to transient thermal application. So yes, you have to define the materials with thermal characteristics, okay, as well as magnetic characteristics and the electric characteristics, if any. Uh, I want to make the electric resistivity depending on the temperature. So first I have to, for the coil, since it's a homogeneous distribution of the current, then I can understand that the temperature will be homogeneous there. I will create a sensor that compute the mean value of the temperature on this coil region, and this temperature of the coil I can create, for instance, directly a new parameter, or I can use it directly on my material flux copper, where I have the electric resistivity depending on the temperature, and here I can use the sensor, the mean value of the temperature computed through the sensor, so I can iterate and update the resistivity of the electric resistivity of the copper according to the temperature computed each time step. Okay, so this is for the, the copper of the coils. But remember that I defined this part as a solid conductor region. So I have to compute the Joule losses inside. Then this core is defined from magnetic point of view as a solid conductor region, and the losses are computed during the solving. That I need to make the electric resistivity of the steel depending on the temperature. So that's why I have first to create a spatial quantity that recover the temperature everywhere on the domain, and I will use it to define the electric resistivity of my steel that I use for this solid conductor region. As you can see, I choose a spatial isotropic resistivity, so I put the electric resistivity depending on the spatial distribution of the temperature. Here the steel will be used for this core region. So everywhere of this core region, the electric resistivity will be depending on the temperature, spatial temperature on this region. Okay, so this is for the core. Then the coil is also defined as a thermal conducting region with the losses computed during the solving, and from magnetic point of view is defined as a cold conductor region with its material. So nothing new here. We have to use exactly the same circuit, and mandatory is really to use exactly the same mesh between this project and the first project where I computed the iron losses. So now what I am going to do is to import the iron losses so I can define the target here. So I have to go to parameter quantities, import spatial quantity. By importation, I will first compute or import hysteresis on the target. I will select hysteresis part of the iron losses. The length is in millimeter, and I imported the density, so it's volumic density of watt per meter cube. Okay, so this is for the hysteresis. And if I make refresh, you can see that it's imported in as a spatial quantity. I can also, I want to import, sorry, so I have to go to parameter again, import spatial quantity by importation, and I will call it EC as well, and always on the target, and I will import the classical part of the losses, and here I have to import the density of the losses. Okay, and I have to make refresh again, and the last one will be the excess losses. I will call it simply EX, and it will be on the target as well, and EX, and it will be watt per meter cube. Okay, then I have all smaller refresh, and I have the three part of my iron losses. What I want to do here is to make eddy current part of the losses of the iron losses depending on the temperature. So I am going to create total. I will call it total iron, and it will be hysteresis losses plus here I have to multiply eddy current losses by 1 plus alpha. I don't remember how the coefficient temperature of the iron. I found in the web internet that it's like this, -6 multiplied by the spatial temperature minus 20 degree, which is the initial temperature. Okay. Here I forgot to make a multiplication, plus the last part, which is excess losses. Okay, okay. Here I have the total iron losses, and I made the dependent the losses, the classical losses dependent on the temperature. So the total iron losses, I need them to be added, not on the core, but on the target. So it's now the target is not simply defined as thermal conduction, but I can add heat losses and defined by spatial formula, and I can select total iron losses I computed. Okay, then I can make apply. So here, this region, I defined it only as thermal conducting region, and the coil is once again the heat source are computed by Joule effect during the solving. Okay, and I need some boundary condition with pure convection here in my case, and my project is done. I have to make a check physics. The material here target is using thermal conductivity, Cartesian thermal conductivity. I will show you that. If I edit, so in the plane xz, sorry, we have the same thermal conductivity, not in the y direction, because it's laminated here the target. So I simply need to orient and the material. And if I make now check physics executed, and here I have simply a warning, so I will not take care about it. I have to define my scenario. Here I define the scenario for simply 3 steps, and I can solve now. Yep. So then, once the project is solved, then we can plot, if we want, the temperature on the target. Here we have only 1 degree and of increase of the temperature. We can plot the temperature on the cores, for instance, as well. Here we have like 14 degrees of increase. What we can plot as well is maybe make again clean selection, select the target, plot the iron losses we imported. It's also possible. So one can change if there is a modification on it, or there is no big impact, and it's normal because the change is not very impressive here. Yeah, so this is how to use iron losses in the thermal computation. I hope that it was helpful for you. Please keep informed on our YouTube channel, and feel free to ask us on the forum or directly to the support. Thanks once again. Bye.